we began this course with some introductory remark that somewhat took a 10,000-foot look at what the course is. The course is introductory circuit analysis, so foundationally, the method of analysis, which are primarily nodal and mesh analysis, should be looked upon as what this entire course essentially is scaffolded upon. We are now essentially at the end, and I wanted to take some time to do another bookend, if you will, to the course, looking at where we are, and also looking essentially at the final exam. I'll start by saying the final exam is not cumulative, in the sense that we are not going to be having circuits that are having DC circuits that with capacitors and inductors with switches that are opening or closing, where we basically had to solve differential equation to get the complete response. Our focus in this last third portion of the course is what we call AC circuits, circuits that have sinusoidal signals. These signals are on for relatively long time, long enough for the natural response to die. And what we are left with is what we call the steady state response of the circuit, with what used to be in the differential equation parlance, the particular solution. Okay, so that's because of that, we've developed an approach that overlay on top of mesh and nodal. That's called the phasor domain, the phasor approach, which we use to solve these circuits without the benefit of solving a differential equation. So that's where we are right now. So that will be the focus of the final exam. Now, having said that, though, you basically, everything we've seen in the first 2 months of the semester comes to play now with AC circuits being applied to AC circuits. So we start with nodal and mesh. Of course, even things like series combinations and parallel combinations, current and voltage divisions, essentially all that comes to back, if you will, and nodal and mesh more formally, Thevenin and Norton models, which we've seen there. Then we spend some time on superposition. Superposition is a requirement if, and I want to underline if and only if you have more than one frequency in the circuit. So we have to apply superposition by frequency as opposed to just by source. So we can actually do all the sources that are one frequency in one solution, and then do the other part of the solution for the other frequency or other frequencies. So these are, and then we concluded this portion by looking at sinusoidal power. Sinusoidal power opened an entire new avenue if folks end up taking more courses in electrical engineering, particularly if you are interested in the power the concentration of electrical engineering, because power becomes really a central generation of power, trying to maximize power, all of that. So these concepts that we briefly introduce, such as power factor, average power, apparent power, looking at power factor lagging, leading, and so on, are really important if you are a power student continuing in electrical engineering. We wanted to give you an introduction. We wanted you to be familiar with at least the lingo, be able to know what they are, the units, and so forth, so that you are armed to go forth here. So, so I just wanted to give you a little bit of overall look of where we are toward the final exam. The final exam will be a 2-hour exam, so I have more time essentially to ask you questions. But my basic philosophy in this class is mesh and nodal. Both of them represent the foundation of the course. And when I say mesh and nodal, I'm looking at a student that goes to this class with me as an instructor should be able to do a mesh or nodal for about 4 unknowns. Anything above 4 unknown, it becomes really superfluous. It's not, you're not learning any more than you are. But 4 unknown, and if we talk about nodal, you immediately have to know how to handle voltage sources that are in circuits. And obviously, counterpart in mesh, It's how to handle current sources. So mesh and nodal are the essence, the foundation of the course. And of course, Thevenin and Norton is what we call a one-port model. In engineering, we need model. We use model routinely, particularly if we want to do more sophisticated problems or sophisticated applications. We want to solve sophisticated application. We use the model to help us go a little bit further than that. And then, of course, the concept of power, which we say. So I hope this gives you a good summary. It's been a pleasure having you in the class, and I hope this has been a learning experience and also somewhat enjoyable, and I get you to think of things that perhaps normally you wouldn't have. I appreciate you being here, and I hope you have a good intercession.